Welcome back to Introduction to Machine Learning. I'm Ludwig Brotbein, and in this video I will speak about pseudo-residuals. We'll speak about the general concept of those pseudo-residuals, and you will see some examples for common loss functions. If we are speaking about a regression task, then the residuals are usually just the difference between the target and the model, right? So it's just y minus f. And what we want to achieve is that these residuals are very small, or so that the sum of the square residuals, for example, would be small, right? The pseudo-residuals are now defined as the negative gradient of the loss function with respect to this model f. So, wow, that's at first sight perhaps super unintuitive how these two things should be related at all, right? So one is the difference between target and model, and the other is the gradient of the loss function with respect to the model. But if you think about it, the model is the thing that we can change. And the question of risk minimization is, of course, how do I have to change the model such that the risk gets smaller and smaller? And the risk is the average or the sum of the losses. So the question is, what do I have to do that the loss gets smaller? So we want to go in the direction of the negative gradient of the loss, right? This pseudo-residual R tilde depends on the target, of course, on the model, and also on the loss function. And perhaps this plot here helps a little bit. So on the x-axis we have the residuals, y minus f. For the, and that's L2 loss, residuals should be 0, it would be optimal, of course. And here we have 1 point with a residual of 1. And if we look at the gradient of the L2 loss at the point of this residual here, we see it's a positive gradient, which means if we want to improve, we would like to have a smaller residual here. Okay, that's a no-brainer because we already know that the residuals should be 0. But the point why I tell you this is to come up with some intuition why these pseudo-residuals are in fact not that much different from those actual residuals, right? Because we want to have them small, should go to 0. We won't have them at 0 usually, because that would be overfitting, and if the hypothesis space even allows such models, but we want to have the residuals very small. Let's have here one example for a best point-wise update, which is a little bit artificial, but it helps understanding, I hope, the relation between residuals and pseudo-residuals. So let's assume we have a model. We already fitted that on some data points. You see here a model, the blue line, and the gray points are the data points. And now we assume that we could update f of x point-wise as we like. So if we look at x equals 0, that's here, f of x would be 0, but y would be 2 point something, right? So we have a positive residual, and we would like to get that residual to 0. So if we only have linear functions in the hypothesis space, that's not possible. Not without making the model very much worse for all the other data points, but if for just a moment we think about a hypothesis space which allows everything, then we could also just say, okay, let's just change the model here at that point so that we have this model here. So it would have this peak here, the model would not be continuous after that, but the fit to the data would at least be better, right? And what we do to achieve this is we go into the direction of the residual. So we take that point here, f of x, and we say, then, so that's the old f of x, which is 0. We just add, let's say, 2.5, and then that's the new f of x. Just at this point here, okay, this only holds for x is 0. And all the other points would be, well, would be as they have been before, so this linear function here. So I guess that's the nicer plot of the same thing I just drew. The pointwise error at this specific x is now 0 because, well, f of x and y are the same here. So we have improved the model considerably, perfectly, but just for x is 0. Of course, we don't really want these very non-smooth functions. So at a later point, we will speak about gradient boosting. And there we don't do these pointwise updates, but we try to come up with a function, this, I guess it's red, this red function here, which is a deviation from the linear function here with some spline, which improves over the linear function, but it's still a smooth model. But you can see the residual here of the red function is smaller at x equals 0 than the residual of the linear function. So what we really want to do, if we look at from the perspective of loss optimizing, is we want to have a function which is better than the old function in the sense of that we go into the direction of the negative gradient of the loss, right? And this is exactly, that's why it's defined that way. This thing here is exactly the pseudo-residual. And we can use the pseudo-residuals in gradient boosting, for example, to iteratively update models with gradient descent in this functional form here. Let's have a look at gradient descent more or less again. Now we speak about parameters theta, not about functions f. And what you see here is the usual definition of gradient descent, right? So we have parameter specification at time point t, and we want to find a new parameter specification at time point t plus 1, or at step t plus 1 in the optimization procedure. And we would like to improve somehow, so we look at the derivative of the empirical risk at this point, and we go in the negative direction. So as you have seen before, if the gradient is positive, then we go to the left, right? And perhaps we would like to scale this gradient by some step size alpha, which could always be the same alpha, or which could also change through time. And hopefully at some point we get to the global minimum of the risk. But if we now look at this nabla of the empirical risk with the chain rule, then the empirical risk is the sum of the loss functions, right? So the derivative of this is the sum of, and then comes the chain rule. First, we derive the loss function with respect to the model, so dl after df. Well, can plug in the current model at that data point x. That's not so important here. And then with the chain rule, we have to take the inner derivative, so we have to derive f with respect to theta. Okay. But if you look at this closely, then you will see that this thing here is exactly, and now I have to cover the minus as well, is the negative pseudo-residual, right? So this means that we can split up the derivative of the empirical risk into two parts. The first part, the negative pseudo-residual, is a loss optimal directional change of the model output. And the second part is derivative of f, which has nothing to do with the loss function whatsoever. Okay, so we look at the loss function and we look at the model, one thing at a time. And that's a very flexible variant and nearly loss independent of gradient descent. Here, final slide of this video, you see just some pseudo-residuals for common losses. So squared loss or L2 loss, if you take the derivative of this and set it to take the negative of this, then the pseudo-residual is exactly the plain normal residual that you know from before. Okay, so that where the beauty comes from somehow perhaps as well, then this is the same. We also have the Bernoulli loss for binary classification. That's then just the difference between the target and the predicted probability. This S function here, right, this is just a sigmoid function or logistic function. Then we have the multinomial loss, which uses the softmax function, But basically the idea is the same as before. We have kind of the true label minus the probability of the true label. And the exponential loss, usually we use with encoding of -1 and +1 after target. Exponential loss is this thing here. And if you derive this with respect to f, then you get this loss here. Okay, that's it so far.